Our next speaker is Steve Holloway of Dialog Semiconductor. Steve is currently Principal Verification Engineer within the IP group of Dialog Semiconductor. He has led the verification of various large-scale consumer SoC projects and has 14 years' experience of hardware verification methodologies including ERM, AVM and UVM, following the wave. His talk is on formal verification of SoC register act. Thank you.
Okay, thanks, Mark. So this is a user presentation. So we at Dialog have been sort of inching our way up the sort of triangle that Abdul presented in his in the previous presentation. So we've been looking at the automatic formal checks and then some of the more value adds or verification apps, and we're also using our informal property checking as well. So we're actually moving all the way up to the top of the sort of triangle. But this presentation is details our experience with the formal verification app, which was sort of presented to us by the Cadence. So we're Cadence formal tool users. And that is that on our SoCs, we have a number of IP blocks nesting in a bus fabric, and we have a specification which says where the registers live in the overall system address map, and within each IP block we have a specification which describes what the registers are, their locations, bit field, purpose, and the access policy. So this is something that we're probably all fairly familiar with. So the issues that we have when we're trying to actually verify the implementation against the specification is, okay, we're going to check that the registers are actually implemented at their specified locations. Are they behaving according to their access policy? But the main issue we've got with this is that this is changing all the time. So our projects are very much our sort of mass market projects are linked in very closely coupled with the customer, with our customers, and we are very reactive to the changes they want to make to the design. So all the way up to a couple of weeks before tape out, they might say, okay, well, we need a register with a new bit of functionality to control another power DC-DC converter or something like that on one of our power management chips, and that comes in very late in the design. So we have to make sure that as an ongoing process, fairly rapidly, can we make sure that the chip is behaving according to specifications within the register map. So I'm not specifically talking about the functionality of those registers within when it's mixed in with the logic of the IP block, but from an external point of view, are they accessible in the way that's been specified? Because we're dealing with that with our other simulations. So this is a point tool or point application of formal for actually validating that the registers are being placed in the correct locations and the correct access policies. So the traditional approach that we've been using for this sort of verification would be our UVM, or constrained random verification environment. So we would have actually have our own description of the system register map, SoC register map. Internally we use a spreadsheet description, but we do export out to IP-XACT, and then we use one of these vendor supply generator tools. So there's obviously a number of those depending upon your CAD vendor. And that would spit out a UVM register model, which then captures the location and the access policy, and you can tack on any special behavior onto the registers in the UVM register model with callbacks, for example. So part of that module would be some checks to make sure that data comes back as you expect, and some coverage to say, okay, we've covered all the values in these registers or all the registers in the memory map, what have you. So there's some kind of tuning that you can do in that side of things. But the point to note on this slide is that in order to make this work, we actually have to put a bit of effort in to write some register sequences to test our expectation of what's in the register model. And we have to hook it up to a bus agent, which is monitoring the traffic going over the bus, hook it into a predictor. And although we've sort of semi-automated the process of constructing our UVM environments, there is some manual work involved in this. So the back end of last year, sorry, let's not talk about that. The other issue here is that in simulation, we can never really have, obviously because of the limitation of CPU time, we can never exhaustively simulate every possible data pattern to every possible register in our SoC. So if you wanted to isolate one particular register and say that, okay, we need to verify that the read-write behavior is correct for all possible data patterns to that register, we need to go through all those combinations of data to that register. So in practice, we can't do this because we don't have enough simulation time to exercise all the registers fully within our map. So we have to make a pragmatic decision about the coverage goals. Are there any interesting values we need to test? Are there any sort of corners that we need to address in our stimulus, and we need to put cover points for those? Okay, so obviously the classic one is when we have 32-bit counters or something like that, what are we actually going to target on those in terms of coverage? So as I was saying a minute ago, back end of last year, I sort of participated in this Cadence register validation webinar, and it seemed that the sort of verification app that they were presenting seemed to be absolutely ideal for this problem that we were having. So the approach that was presented would be to take the IP-XACT specification that we have, place it through another comparable generator, which instead of producing a register model, produces a set of assertions which cover the intent within the specification in terms of the access policy, location, reset value, all those sorts of things which are specified in the IP-XACT. That's things called an iReg val. So it generates a bunch of assertions. We then compile the design into a model that the formal tool can handle, and then we use the formal property checking tool to actually validate whether the assertions that are generated are correct or not. So if we have a problem with debug, we get a nice, easy way of debugging it as compared to a constrained random simulation. And also, because we have a concept within formal proof of non-deterministic data, then this can be used to actually to actually give us a statement of fact around the checking of some of these register checks to say that the checks are correct for all values of data, because this non-deterministic value can take on any value for a register. It's constant throughout the proof, so if you apply that to a write sequence, then sometime later we read back and check against this non-deterministic data. If it's the same, if the check says that the read back data is giving us the same data, then we know the proof is correct for all values of data. So the formal checking categories that the register validation app gives us are the reset checks, so checking the values after reset matches the specification. Read-write checks to check that the read-back value is consistent with the last written value. Read-only checks to make sure that the access policy is honoured, so the value is the same as it was before after a write, and the write one clear check, so there's sort of things about clearing an event register, those sorts of things, so to make sure that if you write a 1 to a bit field, it clears the value on the next read. So in order for this tool flow to work, it relies heavily upon IP-XACT. So the IP-XACT gives us some information which is pertinent to the behavior of the register, but it also puts a lot of things into the vendor extensions. So if you look at the IP-XACT description of a register and one field within that register, obviously we've got the address of that register relative to the base address of the block, the reset value, and we've got the field. We've got the access policy of that particular field, its subsystem width. We've got some vendor extensions. So we've got a HDL path here. There's other vendor extensions that we can use, and this is it's become a bit of a point of contention with us, because although the IP-XACT spec, it's a nice facility, it's a bit of a dumping ground for all these sort of point tools, because the IP-XACT spec itself isn't complete enough to have all these contain all the information we need to actually run these CAD tools. So, and also the other issue is that sometimes CAD tools are not necessarily consistent across the same vendor with the vendor extensions used to describe similar functionality, which is another point. So vendor extensions become a bit of a dumping ground, and I think Cadence have tried to sort of address this by having a sort of merge utility. So you would take tool-specific vendor extensions for the formal register validation approach, such as things as the constraints we need to apply around the DUT, the sequences that we need to create to actually describe the bus protocol access, any specific DUT-specific tickle commands for the formal tool, bundle those up into an Excel spreadsheet, which the vendor provides a template for you. And then you merge that in. So you take your vanilla IP-XACT and produce a tool-specific version of the IP-XACT for that block. Needless to say, we didn't actually use that approach, but we just generated our complete IP-XACT from our sort of spreadsheet description that we had, our in-house spreadsheet. But I think that's quite nice. But I think that that our experience of IP-XACT as being a sort of panacea for all information, it's just really everything's just dumped into vendor extensions, and it's not very usable. And we have to then try and align within the company what we actually put into our own vendor extension. So given that we're actually using this flow, if anybody else is using this flow, there's some tips and tricks that are peculiar for the Cadence register validation, which other people might find useful. So one of the nuances of our register map were that the access policy for some registers could vary according to the bus master that's actually accessing them. So the trick for dealing with this with the vendor extensions, the Cadence vendor extensions for this particular tool, would be to place those registers into two banks. And the idea of this vendor extension of a bank is to say that there's some sideband logic which is effectively selecting a different bank of the registers. So the sideband logic actually would be the H master on the HB protocol in this case. So we have one register here, read only on if the master is host, and it's read write if we have a master of test. So we place the register twice in two different banks in our IP-XACT. And then when it comes to writing the this formal access sequence, then we provide the option of selection of the bank of host and bank of test. And in those sequences, we provide the setting for the HMaster. Then the tool or the application register validation flow will then use those sequences as part of their checking assertions. So this technique can also be used to handle sideband signals which are not part of the protocol, such as lock signals. Another issue that we had with the flow would be the application of constraints. So sometimes we need to, we had some auxiliary logic which is associated with the write one clear behavior of some of the registers. So we have essentially a bit of logic which is at some unknown place buried deep in the DUT somewhere. Wasn't consistent. Designers were using it in different places. So we have to place some constraints around that because it's configurable, and the input to that we would wish to actually make sure that we had cut points and place some register constraints around those inputs to that event generation logic, so that we could run these write one clear checks without it being influenced by any other complex logic in the DUT. So it's cutting that away because that wasn't relevant to the check that we were trying to do. So in order to actually find and constrain these units, then we produced some tickle procedures to actually do some pattern matching within the hierarchy of the design and applying those constraints on that. And then that can actually sit in this auxiliary tickle file which gets pulled in by the formal flow. So then we were then able to create a regression for the entire chip, and I'll go to this one first, with a V manager flow that we're using for our UVM. And this then, we can produce a report from that which gives us all the passes and failures, so we can actually then go off and investigate those failures. And then going back a slide, the tool would produce a counterexample, and rather than going through reams of waveforms in a UVM simulation, it's actually quite simple for us to debug the problem. So you can see that the reset value here expected reset value, you probably can't read that, but that's the expected reset value is FF, and the actual read value on the HB is 0 here, so that failed. And then we can investigate why that is quite quickly. So it's a minimum path through the logic to actually find the failure. So the statistics we found on our last chip that we used, this flow on, which was taped out last week, that's the statistics. 890 registers. That just happened to be the number of properties that the tool generated for those registers, 3,400 about. Obviously, the type of properties it generates depends upon the actual access policies and the particulars of these registers within the design. But the complete test was executed within a very reasonable 6.5 hours, 7 seconds per property. So that's easily doable on an overnight run. That's a sequential run that's paralleled out, so that's the actual CPU time. So you can parallel that out according to the number of licenses you have for IFE. So our sort of experience of this particular flow, it was pretty easy to set up compared to our UVM, previous experiences with UVM, and trying to achieve our register coverage. The counterexample debug is very convenient, quick, and we could execute it as part of the overnight regression. And we did find some issues. So early on we found that, well, throughout the project we could find that people were putting together design snapshots which were actually out of sync with the spec. And early on we did find an incorrect implementation of the access policy overall on some of the registers, so that was fixed. So that was and then we had been running some directed tests and some UVM block level tests as well when we'd actually found that informal. So obviously people didn't believe us, and we had to actually then go and demonstrate that that was the case with our formal flow. So that's it.
Thank you, Steve. Any questions? Sergio?
Sergio Marquez, One Steel Solutions. I didn't understand the extra auxiliary table you had.
Yeah.
Was it like to solve complexity issues or to avoid false fails?
It was to avoid complexity issues, yeah, exactly. And sometimes, yeah, so some of the registers had a lot of logic knocking off the back end of them, and we didn't want to prove, we weren't able to prove that, or we weren't actually interested in the influence of that back into the register block. So we almost isolated the register block functionality within each IP and cut it off from the rest of the design. But some of the status registers we could actually say, if we put rigid constraint on that, then you could say, okay, the status value is always going to be the same.
Thanks.
Karthik from Imagination. Just a follow-up question on what Sergio was asking. How do you ensure that your cutting off of the logic was sound?
It's a good question. I think that's based around pragmatism and some understanding of the design, really. I think that's the answer to that one, and allied with other simulations as well. I think that's the answer.
Martin, Jasper, would you have a stab at quantifying the improvement in or productivity compared to UVM?
Well, I was going to do this. However, I didn't have an exact comparative analysis. All I can say is that the register test, I know that some of the blocks on a previous project, which were UVM only, were taking 3-4 hours for doing register tests. Some of that was mixed in with some functionality. So I don't really have those figures just to do a direct comparison, I'm afraid. So, but I can tell you that in terms of the setup time, that was just a no-brainer to do that. Even if we're still running and we are still running UVM simulations as well.
When you say setup time, does it mean the engineering time?
Creating the environment. All I had to do is write a parser for our spreadsheet format and create the IP-XACT, which looks like the one that Cadence wanted.
Given that you have a way of separating the register part of the block from function of the block, which you must have, otherwise you couldn't ignore the function of the block in your tests, couldn't you just generate all the registers and get it right by construction?
Well, we we do. However, we do that anyway, and yeah, and that's a good argument. And you could argue and you say, well, if you're producing the IP-XACT from the same flow as you're producing the actual implementation, and you made a cock-up in both of them, then then you've got a bit of a problem. But there is, within this automated flow, we have all these little placeholders for user code, and that's where we got the source of our error. So people can put, basically, within the spreadsheet, there's a facility to actually put Verilog in there. Yeah? So this is where we were getting all this kind of random logic affecting the behavior of the registers. So, but I take on that point that things should be correct by construction. But then again, we've got this issue of is it out of line with the spec, and that was the main thing. So when we were simulating the design, is this version 1.0 or 2.4 or whatever it is, and that tells us straight away.
Thank you.